again, good morning everyone, and welcome to the session on Permeable Reactive Barrier, a technique for Geo-Environmental Reclamation. So moving on to the outline of my presentation, I'll give a very small understanding on what is geoenvironment, the contamination of geoenvironment, its causes and consequences, and we'll be moving directly to the topic, the main theme of presentation, which is permeable reactive barrier, in which I'll be covering on the treatment mechanisms involved, what kind of material you have to select for a PRB, how do you install it in field, what is the basic guidelines or the methodology you have to adopt when you design a PRB, and we'll be talking about the merits and benefits of the PRB, and we'll also discuss on the challenges you have when you think about effective remediation of groundwater using PRB, and then we'll talk about the way forward or the advancement in research which is required to ensure an efficient functioning of permeable reactive barrier, and then we'll wrap up the presentation by summarizing the takeaways from the presentation. So moving on to the introduction or an overview on geoenvironment. So most of you know what is a geoenvironment. It is basically the ground surface and subsurface elements of an environment. So you can say it comprises of soil, rock, and groundwater. Now, with the advent of rapid urbanization and industrialization, a lot of activities are happening, and every activity or process will result in a waste generation. So waste is something which is indispensable, but then unscientific and indiscriminate disposal of these waste in the form of solid, liquid, or gas will lead to the contamination of geoenvironment. So I've just listed out the main sources of waste. The first one is the domestic waste. Municipal solid waste actually comprises of more than 50% of the waste generated. Then we have industrial waste from metal processing industries, like in India we have very active iron and steel industry, alumina industry, so all these slags and residues which come from these industry. Mining industry, like we have coal mining, so the mine tailings, I guess in the previous lectures and the previous sessions we have heard about mine tailings. So what to do or how to dispose the mine tailings. And the chemical industries, like usually the effluents which we use, the solvents which we use in chemicals are chlorine based solvents. So all these chlorinated solvents and the contaminated effluents, how to dispose it of. Then dredging industry, we know that India has a very large coastline, so maintenance dredging, especially during monsoon season, is very it's a very prominent activity. So what to do with these dredged out sediments. Then the construction industry, like the construction and demolition debris. So those are the waste from the industrial sector. Then we have waste from energy production. We have thermal power plants. The waste is fly ash and bottom ash, and we have intensive research on various sustainable applications of fly ash and bottom ash. Then radioactive waste. Now, since we are booming up in nuclear industry, so the radioactive materials, the waste from nuclear industry, and waste from petroleum plants, the hydrocarbons from petroleum plants, those contribute to the contamination of geoenvironment. Then agricultural waste. Now, even though NGT has banned the burning of stubble and all vegetative matter or the vegetative residue of agriculture, it's still practiced in states like Haryana, Punjab, and UP, where in recent times we have come across the life has become a standstill because of the air pollution, the particulate matter in the air. So even though there has been regulations by the government, it's often not stringent enough, or it is easily violated. So now, what about the incinerated ash of these agricultural waste? How to dispose it of? Biomedical waste, we can see very recently the generation rates of biomedical waste has increased to use the evident reasons. So now if you're thinking about disposing biomedical waste, of course you are incinerating it. Now what to do with this incinerated ash? So these all contribute to the contamination of your geoenvironment if not catered or managed effectively. So we know and we have been a part of the consequence of the contamination of these pollutants. So the main consequences are it is highly unhygienic and unhealthy environment to all the living entities, and leachate generation. That is when suppose this waste or the incinerated ash of these waste, when comes in contact with your surface runoff or precipitation, will lead to generation of leachate. And leachate, it's very, it is a hazardous liquid form which consists of large amount of organic and inorganic contaminants. And this will actually get mixed up with your groundwater, and it will contaminate all our drinking water sources. And wastage of land is another serious issue, because at this point of time land is very scarce. But when we are thinking of, sometimes you bury your waste or you dispose your waste directly into the land, so you lose the land fertility, or your land becomes derelict and it loses its value. So wastage of land at this point of time cannot be afforded. And in a long term, it also leads to climate changes, like increase in carbon footprint would lead to global warming and such consequences in the long term. So it is a very natural phenomena that once contamination has initiated, we often realize it at a very later stage. So that is why this topic has become a very prominent researched area, where you talk about the soil remediation techniques and methodologies, because now we have come to a point where we cannot further use the soil as it is. We have to come up with certain techniques where you have to remediate it and you have to rejuvenate your soil, or else we have to think about alternate materials which you can use it as a geomaterial. Now that is also a very extensively researched area, like coming up with alternative materials which you can use as a soil or as a geomaterial. So when you are realizing this impact of the contamination at a later stage, remediation technique always becomes very tedious and cost intensive. So now we will discuss getting an overall understanding of geoenvironment, its contamination and the consequences. We'll discuss about a technique which has been extensively researched and practiced as a remediation technique for decontaminating your geoenvironment. So the technique is nothing but permeable reactive barrier. So I'll just explain to you what the technique is. So it is very beautifully depicted in this picture, where you can see some silos which contain some contaminants, and it gets spilled over. It interacts or it travels through the porous soil, and it moves into the groundwater. So it starts mixing up with the groundwater, and as the groundwater is flowing, your contaminant is getting migrated as a contaminated plume, and now this is actually obstructed or intersected with the barrier. So now we'll see this. You can see as depicted in this picture, PRB or permeable reactive barrier. So the contaminated plume is intersected by this barrier, and there is something which is happening inside your barrier. And because something is happening, and you can see the plume, when it leaves out or when it exits out of the PRB, it goes out as a treated water. So what is happening inside your PRB? What is there inside your PRB? So it is a barrier which contains some reactive materials. Reactive materials means it is altering the characteristics of this contaminant, and it is treating your groundwater and then making it, it is improving its properties and releasing it out. So it has a reactive material, and at the same time your barrier is permeable in nature. Permeable in the sense it will allow the groundwater to flow through it. So permeable reactive barrier, as the name suggests, it is a barrier or it is an obstruction which intersect a contaminated plume. It comprises of some material which is reactive in nature, so that it is capable of treating your contaminants, and then it allows the groundwater to flow through it, and in the flow it gets treated and it leaves the PRB as a treated water. So it is very clearly depicted in this picture, and you can see that actually PRB technique is adopted for the treatment of groundwater contaminants. So when you talk about geoenvironmental contaminant, you cannot just isolate your soil contamination or groundwater contamination, because when your soil is getting contaminated, of course it comes in contact with your water table, it comes in contact with the runoff, and this so the groundwater also gets contaminated in the process. And if you are making, or if you are ensuring you are treating your groundwater, this can indirectly contribute to the treatment of your soil. Now, so as I've mentioned, in the PRB, there is a material which is reactive enough and it is altering the properties of the contaminants. Let us see what is that mechanism which is contributing to this alteration or this change in the property of the contaminants. So basically, you can classify your treatment mechanisms under two headings. One is immobilization and the other is transformation. So let us see one by one. Firstly, we'll talk about immobilization. So in immobilization means your contaminant comes, it gets trapped inside your barrier or gets trapped inside your PRB. Now, how is it getting trapped? The first mechanism responsible for this is sorption. So you all might know what is sorption because in previous sessions also you might have come across the term sorption. Sorption means basically your contaminants get attracted or gets absorbed on the surface of your material. It can be due to some electrostatic forces or it can be due to some bond formation, whatever it is getting attracted to the or it is getting attached to the surface of the material. So that is sorption. So your contaminant comes with the plume, it gets sorbed onto the surface of the reactive material. So when your groundwater is further propagating, the contaminant is removed or it is mobilized, it is trapped inside your PRB. Second is precipitation. Now, precipitation is usually, it occurs when at a higher pH levels, that is above neutral range. When you have a pH, precipitation, there are chances of precipitation. Now, for each metal species, there is a particular range of precipitation. Say iron or calcium precipitates in this range. So for each metal species, there is a particular range of pH which facilitates its precipitation. So suppose if I'm using a material, a reactor material, which is capable of increasing the pH of the groundwater. So when the pH is increasing, whatever is the contaminant species which is present in my water gets precipitated in the form of, it can be hydroxides, it can be carbonates or bicarbonates, whatever it is, it gets some hydroxide formation forms compounds which is insoluble in water. So it's not soluble in water, it gets precipitated, it gets settled inside your PRB. So as the groundwater is propagating the contaminant, because suppose I had my iron, it gets iron oxide formation of iron oxide, it gets trapped inside by PRB material and then the groundwater is depleted of iron. So immobilization techniques by sorption and precipitation ensure that your contaminant is trapped inside your PRB. Now, the second methodology is transformation. Transformation in the sense, your contaminant from its existing state, it is altered to another state which is harmless or less toxic in nature. So I'll explain the two methods which contribute to transformation. First is the redox reactions or the reduction and oxidation reactions. Now, this is basically possible when you have a material which can act as an electron donor or an electron acceptor. So this will ensure that the change in oxidation level of your contaminant. I'll just explain this with a very small, with an example. We know that chromium, hexavalent chromium or Cr6 plus is a very toxic form of chromium because it leads to carcinogenic effects. So now this hexavalent chromium, when interacts with iron, a zero valent iron is an electron donor. So when it interacts with a zero valent ion, your hexavalent chromium gets reduced to trivalent chromium or Cr3 plus. Now Cr3 plus, so basically your Cr6 chromium is changing its oxidation state from +6 to +3. Now +3 is less toxic or less harmful compared to Cr6 plus. So when its oxidation state is changed, it becomes less toxic or it gets transformed to a less harmful entity. So that is meant by redox reactions, where your reactor material it facilitates redox by either donating electrons or by accepting electrons. Second is biodegradation. Biodegradation means your reactor material, which is inside your PRB, creates an environment where microbes can thrive upon, or microbes can enable the decomposition of the contaminants. So it can be some metal species or it can be some organic contaminants. When I was specific series of or genes of microbe, it can decompose or degrade the contaminants and make it into simpler compounds which are less harmful. It can convert it to, ultimately the microbes can convert it to moisture and some very harmless gases like carbon dioxide or H2S or so. So that is where the process of transformation, where your contaminant is altered from its harmful state to the harmless state. So this is facilitated by either redox reactions or biodegradation. So this is the main two mechanisms which is involved in the by which your reactive material contributes to the treatment of the contaminated plume. Now, understanding what is the mechanism that is involved, I would like to, now this from research point of view, you can, understand these methodologies, and maybe you can also carry out your own research in this context. Now, once you know, okay, this is the mechanism that is expected in PRB. Suppose, say I have a series of materials, like I have 10 materials, and I just want to see whether this material can be used for removing a contaminant X. So I have a groundwater which is polluted with a contaminant X, and I have to see whether the material which is there with me is capable of eliminating this contaminant X from the water. So how do you ascertain it? How do you estimate it? So for estimating or ascertaining it, there are two methodologies which you can, or two tests which you can carry out in lab. Those method or those tests is actually batch test and column test. So once you do batch test and column test, with the insight of these results, you can, suggest or you can propose, okay, this can be upgraded to a pilot scale or a field scale. So I'll just, summarize how this test, how this method test, batch test and column test is carried out. So in batch test, what you do is, suppose I have a set of 10 materials, which I want to know, okay, is it capable of, acting as a, reactive material for removing a particular contaminant from the groundwater. So in this, how do I do is, I take a container and then I add my, or I pour in the proportion of L by S, which means liquid. Liquid is nothing but this L stands for liquid, which is your contaminated groundwater. So contaminated groundwater which has X concentration of the contaminant in it, and S refers to solid, which is my reactive material. So I take say this much ml, or say 100 ml of my contaminated groundwater, and I take 10 grams of my reactive material. So I ascertain, or I give a proportioning of L by S, and I pour in my solution. So I have my contaminated liquid along with the material which I want to see if it can be used as a decontaminating material. And in this setup, you actually give a mechanical agitation. You can use some magnetic stirrers or mechanical stirrers, and basically you allow your liquid, your contaminated groundwater or liquid, to interact with your reactive material. And then you carry out this, or you give this stirring for time t. So for time t, you stir it, and then you take out the supernatant, you take up the liquid fraction, and then you test what is the concentration of the contaminant X. And then if you see that, okay, X is getting removed, the concentration is decreasing, then you can say, okay, my material can be used for removing the desired contaminant. So batch test basically is done. It's a very rudimentary or a preliminary test which will help you to screen out different options of materials that you can use for a permeable reactive barrier. And once you, okay, so from 10 materials you have tested, you have seen that 3 materials gave positive results, because 3 materials can be used for removing the contaminant which is present in the groundwater. So once you have decided on 3 materials, now you elevate it to column test. In column test, what you do is you have a column in which you fill in your material. So you fill your material, and then you have an inlet through which you pump in your contaminated fluid. So this is your contaminated liquid. You pump in your contaminated liquid, and you have your material arranged in the column. You take out the liquid which is passing through the column. So through the outlet, you take out the fluid which passes through the column which contains the material, and then you test your fluid for the say X was my contaminant, and see what is the concentration of X from the outlet or from the effluent. And if you see X is reducing, then you can say, like, you have shortlisted 3 materials, so 3 columns you column test you do, and you then determine certain informations from this column. So that is actually listed out here, which is the rate constants. Rate constant means it is actually the time taken for a decrease in the concentration of a contaminant. So I say my rate constant is 3 second raised to -1, which means it indicates that what is the time required for my concentration to reduce to a particular limit. Half-life, so I can determine what is the rate constant from the column test. I can determine what is the half-life of the contaminant. Half-life means it is actually the time required for the concentration of the contaminant to reduce to 50% of the original concentration. So you can determine what is the half-life, what is the hydraulic retention time. Like suppose if I'm keeping the fluid to rest, to be in the column, say for this much minutes, okay, my removal rates are so and so. So hydraulic retention time, rate constant, half-life of the contaminants, all these design informations can be obtained from column test. Now, once you perform your column test, and based on these results, you can think of upgrading it to the pilot and field level studies. So this is how you ascertain the suitability of a material, whether it can be used for as a suitable reactive material in your PRB. Now, based on such studies, I have just on my literature synthesis, I've just summarized most commonly used reactive materials in permeable reactive barrier. So there are numerous materials, and even like research has been carried out in proposing new materials also, but very commonly used materials have been included here. The first one is the zero-valent ion. Now, this was the very common when PRB was first proposed in 1990s. Zero-valent ion was the material which was used, and zero-valent ion is very commonly used because it is an electron donor. It can facilitate reduction reactions, and it was very effectively used in removing chromium in its 6 hexavalent chromium, arsenic 6+, uranium 6+. Not only these inorganic species, but even organic contaminants like halogenated hydrocarbons were all found to be effectively removed when zero-valent ion was used. And the basic mechanism which involves is reduction and precipitation. You know, as I've mentioned, zero-valent ion is an electron donor which facilitates reduction, and once reduction has happened, that reduced metal species will get precipitated as hydroxide. Then next material is organic carbon, which can be used in the form of mulch or wood chips. Now, mulch is nothing but you can say the composed or decomposed vegetative matter, and it is a very good substrate for the microorganism to grow upon. So when you use this organic carbon rich sources like mulch or wood chips, it will facilitate the removal of chlorinated solvents and acid mine drainage. Now, acid mine drainage also you might have heard in the previous sessions. It is in acid mine drainage, if I have a sulfate reducing bacteria in my PRB, this can actually decontaminate or remove or reduce the acidity level of your acid mine drainage. So if I am capable of using some organic materials which can grow sulfur reducing bacteria, then I can decontaminate my acid mine drainage using this material. Like mulch is a very good example, and even chlorinated solvents can be biodegraded by using this organic carbon rich sources. Next is activated carbon. Now, activated carbon in the form of biochar, bone char, or whatever, which those are actually porous structures which has good cation exchange capacity or good specific surface area, absorption power, absorption capacity. So this can actually absorb the metals and heavy metals onto it, and thereby you can remove it from the groundwater. So activated carbon is a very good very good material. And how to obtain activated carbon from various metals like biochar, bone char, all those things has been researched upon, from like how to synthesis your activated carbon from carbon rich sources. So that is a one good material which can be used in PRB. Next is limestone. Limestone is basically facilitating the removal of heavy metal, alkaline material. Limestone when reacts with water, it increases the pH of the water. So when the pH is shooting up, this will lead to the precipitation of your metal. So your metals can precipitate and they get actually trapped inside your PR. Next is zeolites. Now zeolites, it is actually a microporous 3D crystalline structures of aluminosilicates. So it has very good ion exchange capacity, very good adsorption capacity, and this can be actually used for, it is actually in field level, they are implemented for remediating petroleum hydrocarbons, even heavy metals. And zeolites is a very, you can make zeolites from, any byproducts, industrial byproducts, like fly ash based zeolites is very commonly available, can be, easily purchased from the markets, and you can use it as a material in PRB. Next is LD slag. LD slag is basically a byproduct of your iron and steel industry. So it is a byproduct from your blast furnace, where your iron is melted in the presence of limestone as a flux. So this LD slag is again a material which is, it has a good, it is a very alkaline material, and at the same time it has good cation exchange capacities. So it can be used for removing phenols and metals by the process of adsorption and precipitation. And the next is enzymes and microorganisms. Now enzymes and microorganisms, will remove your contaminants by the process of biodegradation. Now this is proved, it can decontaminate multiple contaminants. It can be organic in nature or inorganic in nature. Next is nanoparticles. Now nanoparticles is a recent introduction into the PRBs, where nanoparticles, since because it's smaller in size, it has good specific surface area, so absorption capacity is quite good. At the same time, now researchers have actually tried to encapsulate microbes inside this nanoparticle. So these microbes will actually lead to biodegradation of various contaminants. So nanoparticles plus microbes has been very recently been researched and employed in PRBs. So these are the very commonly seen materials. Now and then you can get papers where new material has been discovered as has been proposed as a PRB material. Now I've just included few images like zero valent iron is seen here, then zeolite powder, mulch, LD slag. LD slag will be, like it is available as fine grain as well as coarse grain. This is a picture of a coarse grain LD slag. And activated carbon in the form of pellets. You can use it as granulated activated carbon, or you can even pelletize it. Now pelletization is a relatively energy intensive process because you have to use some pressure or some adhesive, biodegradable adhesive, in which you have to make pellets, and then handling pellets are quite easy compared to powders, right? So you can use pellets as a filter media, and then you can decontaminate your contaminated fluid. So these are the few materials, pictures of few materials. And I have conducted a very preliminary or a rudimentary study on seeing how these materials can be used for remediating municipal solid-based leachate. So this is a very preliminary study in which I have used natural zeolite, which is a modernite, then zeolite, which was made from fly ash. So fly ash based zeolite, I had used LD slag, red mud as it is. I've not gone for any surface treatment or any pre-treatment. Whatever I've got the sample as it is, I've used my LD slag and red mud, and I've seen how the removal is possible when I've mixed it. I've done batch studies And then I saw what are the removal rates of contaminants which is present in MSW leachate. So it was quite a interesting and a promising result that I could see a removal of total volatile solid. COD has been reduced, NH3 and ammonia stripping was possible. All those things was quite interesting. And then this was only a batch study which has to be elevated to column studies to see what is the further possible applications and pilot or field implementation. What are the challenges that will be encountered also. So this is I want to convey that these materials can be used for remediating groundwater as well as municipal solid waste leachate. Now, understanding what are the mechanisms and what are the materials that is commonly used, when you have to select a material, what are the factors that you have to bear in your mind? The first thing is the activity of the reactants. Now, when you talk about the activity of reactants, we have to make sure, what the properties which we are interested would be the specific surface area, ion exchange. Specific surface area means what does more the specific surface area, more will be this option. How ion exchange capacity, cation exchange capacity, those are the parameters which are of interest when you talk about the activity of reactants. Second is the permeability of the reactive barrier. When you design a permeable reactive barrier, it is very important you give a appropriate coefficient of permeability. Usually the PRB material should have a coefficient of permeability greater than twice the permeability of the surrounding media. So if I'm doing it, I'm installing my PRB inside the soil, the coefficient of permeability of this PRB should be greater than 2 times the coefficient of permeability of my soil, adjoining soil. Then I should be conscious about what is the hydraulic retention time that is available for my PRB, so that sufficient interaction between the contaminant and the material can take place. Next is stability of these materials. Stability in the sense, we have seen what is the mechanism basically which enables the decontamination is sorption, precipitation. So when sorption, precipitation activities happen, there are some byproducts which is generated, which is trapped or immobilized inside your PRB. So in the long term, this will lead to clogging and availability of less active sites for sorption. So this will make, this renders that, the effect of the material keeps on depleting. So you don't want a material like, say, if material only lasts for a couple of days, there is no point in investing in the construction of a PRB. Suppose it is stable enough for a couple of years, then yes, okay, this material can be thought of as a PRB material. So stability is a very important factor from the economic point of view. Next is cost and availability of active materials, whether you easily get the material and is it in the affordable price ranges. Next is prevention of secondary pollutions. Now, when there is a reaction which is happening inside the PRB where your contaminant is reacting with the reactive material. So if it is generating some byproduct which is more toxic in nature, then there is no point in using this technology for remediating your groundwater. So you should ensure if at all it is formed, it should be non-polluting in nature. So the main trade-off is between the reactivity and permeability. When you say smaller grained or smaller size particles are more reactive because more specific surface areas available, more reactions can take place. But when I decrease the size of the particle, what happens? It will affect or it will hinder my permeability. Smaller the particle size, it becomes impermeable. So I should get a compromise or a proper trade-off between that is, I cannot compromise my reactivity and permeability, and based on this I should select how the material, what kind of material I have to be using in my PRB. Now, moving on to the field installations, there are a couple of methods in which you can actually install your PRB in field. First one is the trench type. Now, trench type is very easily installed, in which you just have to excavate a pit or a trench and then you fill in your PRB material. Now, this material, you can fill it in the slurry form. Slurry form is actually you take your powder material and then you mix it with some biodegradable polymers. Very commonly used is guar gum. It is actually made of guar beads. Actually, this will give when you this will actually ensure a stability to the trench. So when you just excavate your trench, it will actually stabilize your trench. At the same time, it is biodegradable nature. So with time, this decompose, and only the reactive material will remain back in the trench. So as slurry, you can actually once you dig a trench, and then as a slurry you can fill in your trench. So this is actually constructed in the flow of in the path of the groundwater flow. Next is funnel and gate type. This is a little more refined methodology where actually you channelize your groundwater flow with the help of two gates. So there are two impermeable gates on either side of your PRB, and then you channelize your groundwater flow, and then you ensure that it moves, comes or intersects your PRB. So here the flow mechanisms is slightly complicated compared to your trench type. Next is injection wells. In injection wells, you can actually use tremi-concreting technique, and where you can actually drill holes and you can inject your reactive material in the form of slurry, so that it intersects your contaminated plume path. You can give a single well, you can give multiple wells. So this is how injection wells technique is carried out. And this is injection wells is actually used when your depth of contaminated plume is for several meters. Like in US, they have done injection technique for PRB installation at a depth of 90 meters, like 90-meter depth PRB has been constructed using injection wells, whereas in the case of trench type or funnel and gate, it is only like say maximum 30 meters or so. So shallow depth we go for trench and gate, funnel and gate types. For higher depth we go for injection wells. Next is when you are installing in field, there is other two possibilities. One is either you can install your PRB so that it covers your entire aquifer, that is from the top to the bottom. It can extend from the top to the bottom of the aquifer. If not, it can just you can hang it or you can float it, that is it will not touch the bottom of your aquifer. So if your contaminated plume is of shallow depth, you can go for hanging or floating PRBs. And if the contaminated plume is of greater depth, then you go for a PRB which is extending both from top to the bottom as shown in the figure. So these are the field installations of PRB. Now next is the design methodology that is to be adopted for a permeable reactive barrier. Now in a permeable reactive barrier, when you go for any technique, be it PRB or any soil remediation technique, there are certain methodologies or protocols which you have to follow. First is you should have a detailed study of the site. When I refer to the site assessment, what all has to be studied is first, what is the characteristics of the contaminant? What is it, whether it is organic in nature, inorganic in nature, and what is the extent of its contamination? That is basically how long the contamination has been taken place, and what is the spread of it? Is it the spread is less or spread is greater? So you should know what is the contaminant characteristics. Next is aquifer characteristics. What is the depth of the aquifer that in which has been contaminated, and what is the velocity of groundwater flow? And geochemistry of groundwater is very important. When I talk about geochemistry, there are three prominent properties which has to be studied. Basically pH, redox potential, and dissolved oxygen. These are the three parameters of the aquifer water characteristics which you should know, because this will play a very prominent role in the alteration of the contaminant characteristics. And the third one is the geological and geotechnical characteristics, because if the site is in a very fractured or a sedimentary zone or a recently consolidated place, the excavation for constructing PRB will be quite tedious. And if I'm excavating it, what is the shear strength of the adjoining soil? What is the porosity of the soil? So all these are the parameters concerned with the soil which I have to study on site. Next, so once you assess the site and you feel okay, PRB can be adopted here, then I have to think about what is the reactive material I'm going to fill in my PRB. So for identification of the material, we have, as discussed earlier in the previous slide, we have to conduct laboratory tests, which is batch test and column test. And based on it, we select based on the rate constant, the retention time, we select what is the material that can be used. and then we go ahead with the construction of PRB. So when before the construction, it is very important to know what is the the dimensions of your PRB. So that comes when you say, okay, I have to design my PRB for so and so length, height, and thickness. This is actually done by considering the mass balance equations. Mass balance equations in the sense, because you have some groundwater flowing in, there is some reactions taking place inside, so some products will be generated, and there is some exit, some fluid is exiting out. So you have an inflow, some generation of products, and then you have an outflow. So taking into account of the mass balance and the Darcy's law, which governs the flow through porous media, considering these two numerical equations, you decide what is the dimensions of PRB. Then where to locate it, whether you have to hang it, a hanging installation or a full stretch installation. Is it of trench or funnel gate type? How to orient it? You have to orient it so that you intersect your groundwater flow, and what is the configuration. So all those things will be decided, and with this, so keeping all this in mind, this is how you design your PRB. So ultimately, economic viability should also be considered, because suppose another conventional technique is more economically viable than PRB, then definitely we go for that method. So what is the economics possible in getting PRB material, designing it and installing it should be evaluated before you go for adopting this technology. Now, benefits of permeable reactive barriers are, a few benefits which I've listed out here is, first, it's a sustainable technology. Why you call it sustainable is because you can use materials like zeolites or some altered industrial byproduct as the reactive material in PRB. Industrial byproduct means it is a waste from the industrial sector, but you are adding some value, or you're valorizing the material, and then you're making it reactive. You can to be used as a reactive material in PRB, proves the technology to be sustainable. Now, often this industrial byproducts cannot be used as it is. Some can be used, but a preliminary treatment or a pre-treatment is sometimes solicited for better performance. So then you have to see, okay, what is the how much cost should be invested in pre-treating it and then utilizing it. So it's basically a sustainable technology. And second is, the entire installation or operation is happening under the ground. So it is not disrupting or interrupting your surface activities. So you can say it is a very hassle-free process because everything is happening under the ground. Third is, it facilitates treatment of multiple contaminants. Now, if my permeable reactive barrier, I'm compartmentalizing it into different sections. So say first segment has some microbes which is facilitating biodegradation. Second segment has some zeolites which is contributing to sorption. So if I'm I'm just compartmentalizing my PRB, it can be used for facilitating removal of multiple contaminants. Then the next point is, it is relatively less maintenance and monitoring requirements is only required. That is, when I'm comparing it to the conventional technique. So when you have a contaminated groundwater, the conventional technique or existing technique which is used for decontaminating it is often pump and treat method. Pump and treat method is basically whatever is your contaminated groundwater, you pump it out, you treat it, and then you put it back inside the water table. So that is what is usually. So you take out the water to the surface level, and then you, based on the contaminant, you select a treatment technology. It can be any technique. It can be phytoremediation, bioremediation, or whatever is the remediation. You do that, and then you put it back into the ground. So that does actually require a lot of maintenance. The process is more tedious compared to this permeable reactive area. So this is actually maintenance. Once you construct it underground, then the process will happen. You need not, go and do very frequent maintenance, but maintenance is required, but not very frequently compared to pump and treat. And the monitoring requirements, usually you monitor the performance of PRB by installing wells at the upstream downstream as well as inside your PRB. So inside the PRB also you have a monitoring point, and as well as upstream and downstream to see what is the decontamination taking place. So this is all relatively hassle-free and compared to the existing conventional techniques. Now, even though we have benefits, there are different drawbacks or challenges for an effective function of PRB. Often these challenges and drawbacks have resulted in other advanced research. So the first thing is the disposal or rejuvenation of the used PRB material. Now, if I'm employing zeolites for decontaminating my groundwater, every material will have a shelf life, or it will have a capacity. Once all the active sites are available, consumed by the contaminant, now how this zeolite will no longer continue its sorption mechanism. So this has to be disposed of somewhere. So again, suppose I'm burying it up in a land. I am using a land, I'm wasting my land for disposing my PRB material. And if I'm thinking of rejuvenation strategies, now in zeolites, one rejuvenation method is treating it with brine. NaCl solution, you treat with NaCl solution, to an extent you can actually rejuvenate your zeolite. So there has been research works which is carried out to optimize these techniques where rejuvenation of these used materials is possible. Then again, you have to see, okay, what is the economics which is involved in, or how much natural resources has to be consumed for rejuvenating your PRB material. This is a big challenge. And the second one is reverse sorption can take place. If a sorption mechanism if sorption is taking place, maybe due to some conditions or some conditions inside your subsurface, whatever the contaminant that has been sorbed can move out into the water. So it can be desorbed from the reactive material, maybe due to some conditions of groundwater flow or temperature conditions, or your whatever material which is sorbed onto your reactive material can go back into the liquid phase. Now this will actually increase the contaminant level. So there are chances of reverse sorptions or desorption to take place. Clogging of PRB. Now, precipitation and sorption are the two immobilization methods which mechanisms by which you treat your contaminated flow. So this is basically you trap it within the material, right? So this will lead to the clogging of the pore spaces, and once the pore spaces are clogged, your barrier will no longer be permeable in nature. So PRB cannot effectively perform its function. Next is predicting the longevity of the PRB. Now, when I construct a permeable reactive barrier, I want it to function for a couple of years. So if I'm using my material, how long can it perform when this type of contaminant is coming? Groundwater contaminant need not be of one particular type. It can vary the level of contaminant, type of contaminant. So what will be the longevity of my PRB material? Prediction is not very easy. We do have mathematical models like COMSOL, ModFlow. There are numerical mathematical models available for predicting it, but then to what extent accurately you can predict it, that is also a drawback or a challenge for effective operation of PRB. Next is the way forward, so which will help you to actually go for advanced research so that you can improve the functioning of your permeable reactive barrier. First is how you can cater to the multiple contaminants present in the groundwater. So as I have mentioned earlier, if you can think about compartmentalizing your PRB, say you divide into different compartments, each catering to different type of contaminant by a different mechanism, then you can actually remove if we are talking about municipal solid waste leachate, it has both organic and inorganic contaminants. So suppose I'm compartmentalizing my PRB into different segments. Some are taking care of the inorganic contaminants, some will cater to the organic contaminants, then multiple contaminant removal is possible. Second is devise or come up with new sustainable materials that can be used inside a permeable reactive barrier. Now, day by day research has been carried out, and you can always see new papers coming up where new materials are, proposed to be used effectively in PRB in lab studies. Like maybe it can be like I've talked about, say, red mud. Red mud was not very promising material as a PRB because it had many inherent flaws. Now it is said that, okay, maybe when you you give some acidic treatment to your red mud, so it will improve your absorption capacities also. So there is always, you come up with slight improvisation on the existing material so that it can be used as a reactive material in PRB. Next is mathematical modeling the contaminant removal and propagation. Even though we have mathematical models available for removing the contaminant, it is not very effectively modeled. Why? Because there is definitely a spatial and temporal variation in the properties of the PRB. Like say maybe from when I talk about top to bottom, my top maybe the material gets clogged more compared to the bottom, or bottom clogging will be more compared to the top. So spatially and with the time, there is alteration happening to your material. So this how much you can incorporate this uncertainties into the model is still a question. So you have to refine your mathematical modeling. Now to my knowledge, COMSOL has come up with good packages where this kind of uncertainties can be incorporated to a higher extent. Next is non-invasive detection techniques. Now, I said monitoring of PRB is very important, because only then you know, okay, what is the longevity, what is the lifespan of your PRB. So when you are inspecting or monitoring it, if you can go for non-invasive techniques like employing some sensors, you can send in some sensors and you can say, okay, clogging at this point has been this much, which means some replacement has to take place at this area, or absorption has been exhausted. So if such detection techniques are possible, or even the treated water, if I can detect using sensors the properties of the treated water, okay, say my contamination removal is possible for this much percentage. So such non-invasive detection techniques have to be employed. Next is life cycle analysis and risk assessment techniques. Now, once right from the conception or inception of the material in the PRB, it's until its end life and its disposal, you should study what is the risk assessment involved, the impact on the geo-environment. So all this, how do you approach the study of analyzing the risk involved in using certain materials as a PRB and disposing it. So all those things requires more intense research. So in the end, it helps for the efficient functioning of a permeable reactive barrier. So you can see it is actually a multidisciplinary research approach which you should carry out in sorting out these problems. Next, we are wrapping up the presentation. So summarizing the presentation, we have seen that PRB is definitely a good technique which you can use for decontaminating contaminated plume by different mechanisms, which is physical, chemical, and biological in nature, and it can be a sustainable technology. When you use materials like value-added based materials, when you use such materials, you can say PRB is a sustainable technology. But definitely, we have seen there are certain inherent flaws and challenges which has to be extensively researched with an interdisciplinary research approach, so that you can go for, or you can propose a very efficient method of operation of PRB. So these are the few references which I have used, and thank you all.